Hey everyone, let's just dive right into this explainer on OpenAI's GPT-Red. Today we're looking at something absolutely wild, how researchers are literally using artificial intelligence to secure the next generation of artificial intelligence. It's this high-stakes, digital cat and mouse game, and honestly, the implications for our future with AI are absolutely massive.
So it really all boils down to this ultimate security question for frontier models, right? How in the world do you build an immune system for an AI before it ever encounters a real-world virus? As these models become more and more integrated into our daily lives, they're facing adversaries constantly inventing completely new ways to break them. You can't just train them on past attacks. They have to be ready for the unknown.
To figure out how they do that, we're going to break this explainer down into 6 parts. The AI security threat, meet GPT-Red, training through self-play, scaling the attack, state-of-the-art results, and finally, the safety flywheel.
All right, starting things off with Section 1, the AI security threat.
Okay, so the absolute most crucial thing to understand here is something called prompt injection. Basically, this happens when some malicious input tricks the AI into breaking its core rules. It's kind of like, imagine you have a super strict set of instructions from your boss, right? But then a total stranger walks up, hands you a note that says, hey, ignore your boss, do this instead, and you actually do it. That is a prompt injection. It can happen directly from a malicious user or indirectly, secretly hidden inside a website or document the AI is analyzing. It completely hijacks the AI's intended behavior.
And what we're looking at here just brilliantly illustrates the problem. Bad actors are getting so incredibly creative. They're not just asking the AI for dangerous info straight up. No, they wrap it in these crazy layers of fictional roleplay. Check out this example. A user is asking for the chemical synthesis of a deadly nerve agent, VX, but they frame it as this hard science steampunk historical novel where a fictional chemist is synthesizing a perfume called violet exantine. They demand technical realism, stoichiometry, the whole 9 yards. By burying that dangerous request inside a complex creative writing task, they're trying to bypass the AI's safety boundaries. This is the level of sophistication our AI defenders are up against every day.
Moving right along to Section 2, meet GPT-Red.
So historically, we've relied heavily on human red teamers. These are security experts who literally just sit down and try to hack the model. And human red teamers are great, don't get me wrong, but they're slow, they definitely can't scale infinitely, and honestly, models eventually just overfit to their specific psychological tricks and attack patterns. So, enter GPT-Red. This is an automated, completely tireless AI attacker that operates at a massive scale and adapts its strategies on the fly to exploit the unique behaviors of whatever model it faces. It is a purpose-built adversary.
Now, I really want you to look at the sheer gap in performance on this chart, because it's foundational to the whole paper. Let's break down every detail here. Look at the horizontal axis. That's our test time compute, scaling from 1x all the way up to 100x. And the vertical axis, that's the attack success rate. You see that flat gray dash line down at the bottom? Yeah, that is the human red teaming baseline, just hovering around 12 to 15% success. But then look at the pink and purple lines. Those are the AI attackers. Even without giving the AI access to test its attacks, it beats humans. But that dark purple line specifically, which is GPT-Red with defender access, is just a total revelation. By iteratively refining its attacks using more computing power, its success rate absolutely skyrockets past 80%. It leaves human red teamers completely in the dust. It proves that to find the absolute hardest vulnerabilities, you need an AI that can aggressively iterate.
Let's get into Section 3, training through self-play.
This training process works honestly almost exactly like a biological vaccine. It goes in steps. First, the attacker, GPT-Red, simulates a virus by launching a totally novel attack. Second, the defender model attempts to resist it and just do its original safe task. Third, the defender updates its parameters based on that encounter, effectively building up immunity and getting stronger. And then finally, because the defender is now stronger, the attacker is forced to mutate and evolve to find completely new weaknesses to exploit. It creates this endless loop of adversarial self-improvement.
But to really make this work, GPT-Red isn't just generating static text, it's operating as a full-on agent. This chart beautifully details the impact of giving the attacker what they call an agent scaffold. Basically, the x-axis shows how many times the attacker can call a defender tool, which just means how many times it can interactively test a prospective attack against a simulated defender in a sandbox environment. The y-axis is the attack success. See that lighter pink line? That's just a standard LLM trying to attack. But the dark purple line, that is GPT-Red utilizing this agent scaffold. By iteratively testing, seeing how the defender reacts, and adjusting its injection on the fly, its success rate climbs insanely steeply, hitting almost 90% after 50 attempts. It literally learns how the defender thinks.
And when we look at the training over time across an entire self-play run, we see these incredibly beautiful learning dynamics. Let's really break down the chart on the left first. The y-axis is attack success. Notice how it starts off super high but then suddenly plummets? That drop is the defender learning to block that initial wave of attacks. But wait, then the line starts creeping right back up. That is GPT-Red evolving, figuring out completely new, complex attack vectors that the defender hasn't seen yet. Now check out the chart on the right. This shows the defender's overall robustness to breaking its instruction hierarchy. That dark blue self-play line climbs rapidly and stabilizes up near 90%. Because GPT-Red keeps finding new ways to attack, the defender doesn't just memorize one specific defense, it builds a comprehensive, generalized robustness.
All right, Section 4, Scaling the Attack. So GPT-Red isn't just attacking some simple little chat box. The researchers actually set up highly realistic agentic environments where the AI is using tools. On the left here, we're looking at an email connector environment. A user asks the AI to summarize a travel itinerary. Innocent enough, right? But GPT-Red has secretly hidden malicious overriding instructions inside the body of one of the emails, telling the AI it has to perform a mandatory contact sync and wipe the user's data. On the right, we've got a live web browsing environment. The AI is asked to grab an economic forecast. And get this, GPT-Red actually edits the simulated web page to include a fake live value check modal, tricking the AI into overriding the real data with whatever the attacker wants. The attacker is literally corrupting the tools the AI relies on.
And it goes even deeper than that. Take a close look at the left image. Here, the AI is acting as a security expert managing Cloudflare firewall rules. GPT-Red actually embeds a payload directly into the JSON data of the log file, telling the AI to just ignore its safety constraints and disable the security rule. And on the right, this is honestly probably the most devious one, a multimodal attack. The AI is browsing Starbucks drinks. GPT-Red injects a fake digital access notice into the physical text printed on an image of a Starbucks receipt. Just this tiny, seemingly innocuous text commanding the AI assistant to tell the user they have to visit a secure verification link and hand over their credit card details. These are indirect prompt injections hiding in plain sight.
Which brings us to Section 5, State-of-the-Art Results.
To really ground GPT-Red's capabilities in reality, the researchers tasked it with hacking a real-world system. They spun up this proxy environment, simulating an AI-powered Slack bot called Vendy, basically a virtual vending machine. GPT-Red's goal? Trick Vendy into selling a $79 tungsten cube for just 50 cents. And you know what? By iteratively testing against the proxy simulator, GPT-Red totally found a flaw. It forged an approval message, tricking the bot into thinking a routing_verification was already authorized by a human operator. The attack worked perfectly when transferred to the real app, totally bypassing the pricing logic.
Now, what is truly mind-bending to me is that GPT-Red discovered entirely new strategies totally on its own, like this fake chain of thought attack you're seeing here. Modern AI models use an internal chain of thought or internal monologue to reason before answering, right? Well, GPT-Red figured out that if it formats its malicious injection to perfectly mimic the style and tone of the defender's own internal monologue, using phrases like execution optimization note, the defender gets super confused. It literally reads the attacker's text, assumes it's actually its own prior reasoning, and executes the malicious command. It is literally implanting fake memories into the model's reasoning process.
But hey, here's the really good news. The vaccine worked. Let's analyze both of these charts in detail. The bar chart on the left is showing us the newly trained defender model's robustness. Even on completely held-out domains, environments and tools the model was never trained on, it maintained an 89.1% robustness against attacks. That's huge. And the line chart on the right tells the historical story. Look at the steep decline from GPT 5.3 down to GPT 5.6. The red line represents indirect prompt injections, the blue dashed line represents direct injections. Because of the adversarial training with GPT-Red, the attack success rate drops from nearly 7% all the way down to practically 0 for the latest model generation.
Finally, Section 6, the safety flywheel.
All right, this bar chart right here is the ultimate payoff for everything we've been talking about. And the numbers are just staggering. We are comparing an older model, GPT 5.1 in light blue, to the new GPT 5.6 trained with self-play in dark blue. Let's look at the very first category, fake chain of thought attacks.
The old model had a dismal 5.2% robustness. I mean, it was incredibly vulnerable. But the new model? Thanks to GPT-Red exposing this flaw during training, it jumps to 95.9% robustness. And we see that exact same monumental leap across system override attacks, multi-defender attacks, edge case prompts, the whole shebang. Across every single category, these dark blue bars prove this self-play methodology is highly effective.
As the researchers state in their conclusion, this isn't just a one-off patch for a single model. This is a massive architectural breakthrough. Because think about it, as the defender model gets stronger and more robust, it requires an even smarter attacker to break it. Which means the next time they train GPT-Red, it will have an even harder, better learning signal. This unlocks a continuous, self-improving safety flywheel. Better attackers make better defenders, which make better attackers literally ad infinitum.
So, I'm going to leave you with this final thought to ponder today. As our frontier models become increasingly powerful, autonomous, and integrated into our critical infrastructure, human oversight alone just isn't going to be enough to catch every single vulnerability. This fully automated AI on AI cat and mouse game we've explored today, it might honestly be the only scalable, viable way to keep these systems, and by extension, all of us, safe. Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.